Chapter 9, Section 6, Dilations. So under a dilation about a fixed point, and for us it's usually going to be about the origin, distance is not preserved. So it's not an isometry, it's not a rigid motion. However, angle measure, collinearity, and midpoint are still preserved under a dilation. So the angles will still stay the same because they are literally going to be similar figures, the preimage and the image. So here's our official definition. Dilation is a transformation that produces an image that is the same shape as the original, but is a different size. So it's not an isometry or a rigid motion. It forms similar figures. The rule is you're going to have a scale factor k. The center of dilation is assumed to be the origin unless it's otherwise specified. So a dilation of k, you multiply the x value by k and the y value by k to get your new coordinates. A dilation is an enlargement if the scale factor n is greater than 1, and it's a reduction if the scale factor n is between 0 and 1. So it can't be negative. So basically, if it's a fraction or a decimal, it's a reduction, and if it's a whole number or something that's greater than 1, even if it's 1.5, it's an enlargement. This example should be done on graph paper. So we have our pre-image. 0, 0 is A. 3, 5 is B. And negative 2, 5 is C. So using a straight edge, connect your points, your vertices. And we want to find the image of ABC under a dilation of 1/2. So that's going to be my A prime, B prime, C prime is going to be my dilation of 1/2. And under a dilation of 2. So here we're going to have, this is an enlargement. And this is going to be a reduction. You don't need to specify this on a test, but just so you can see the difference here. So this will be our A double prime, B double prime, C double prime. So under 1/2, 0, 0 is going to stay 0, 0 because half of 0 is just 0. B is going to become 3 divided by 2. So 3 times 1/2, which is 3 over 2, which is the same thing as 1.5. And 5 times 1/2, which is going to give us 2.5. C is going to be 1/2 of negative 2 is negative 1, and half of 5 is 2.5. Then we plot our points and connect our vertices, and you can see that it was reduced by half. The enlargement by 2, again 0 times 2 is just 0, so that point stays. It's about a fixed point, and that fixed point is the origin, so that's why 0, 0 is staying where it is. 3 times 2 is 6, and 5 times 2 is 10. And negative 2 times 2 is negative 4, and 5 times 2 is 10. And then we're going to plot these new points. So we have 0, 0 is our A double prime. 6, 10 is our B double prime. And negative 4, 10 is our C double prime. And then again, using a ruler, a straight edge, connect our vertices. So there we have our enlargement, which is our double prime, and our reduction, which is our single prime. Section 7 talks about similarity transformations. So copy this down and make sure this example is on graph paper. You don't need 2 separate sheets of graph paper. You can just have this final image after we go through all of the steps. So triangle DEF has vertices D, E, and F. Plot these points on a coordinate plane. They're asking what is the image of triangle DEF when you apply the composition, a dilation of 1.5 composed with a reflection across the y-axis. Well, this means that we're going to do the reflection across the y-axis first. So that's what we have here. So we're going to take triangle DEF and reflect it across the x-axis, and that gives us these new coordinates. Then we're going to do the dilation of 1.5 to our new triangle, so to D prime, E prime, F prime. So negative 2 times 1.5 gives us negative 3, 0 times 1.5 gives us 0. Negative 1 times 1.5 gives us negative 1.5, and 4 times 1.5 gives us 6. Negative 4 times 1.5 gives us negative 6, and 2 times 1.5 gives us 3, and we plot those points on our coordinate plane. Then we're stating the vertices of the image after the composition of transformations are these points. And we would just state that triangle DEF is similar to triangle D double prime, E double prime, F double prime. And the reason is because it is made up of a composition of transformations which preserve angle measure but not distance. So the triangles are not congruent, however, they are still similar because of the dilation. Describing transformations. Again, make sure you have the coordinate plane so we can plot these points as we go. What is a composition of rigid motions and a dilation that maps triangle RST to triangle PYZ? So we want to start off with triangle RST and plot these points on your coordinate plane. So we have 1, 1 is R, 1, 3 is S, and 3, 1 is T. So let's write this off to the side. R is 1, 1, S is 1, 3, and T is 3, 1. We want to get that to turn into PYZ. So what composition? Well, we can see that from this triangle to this triangle, there was an enlargement. So let's write the coordinates of triangle in the same order. So R is the right angle, so P is the right angle. And then we'll have Y for S and Z for T. Well, P is negative 2, negative 2. Y is negative 2, negative 6. And Z is negative 6, negative 2. Well, we can see already that we multiplied by 2. That's what's happening here. But what else is happening that's changing these values? Well, it appears that triangle RST was rotated and then enlarged to create triangle PYZ. To verify this composition of transformations, we need to rotate the triangle 180 degrees about the origin first. So this is our rule. We negate the x and we negate the y. And that is what's happening here. So first we do the rotations and we get these coordinates. Then it appears to be about twice as large as RST. So we're going to multiply those new coordinates here by 2 using this rule. The vertices of the dilation of triangle R at R prime, S prime, T prime match the vertices of triangle PYZ. Therefore, a rotation of 180 degrees about the origin followed by a dilation with a scale factor of 2 maps triangle RST to triangle PYZ. And they're similar here, again, because a dilation doesn't preserve distance, but it does preserve the angle measure, so the triangles will remain similar. So notice that the figures in problems 1 and 2 appear to have the same shape but different sizes. Compositions of rigid motions and dilations map pre-images to similar images. So when it was just rigid motions, they map pre-images to images that are congruent. But when you add a dilation in, it makes them similar. So for this reason, they're called similarity transformations. They give you another way to think about similarity. So we've talked about in the past how a dilation of an object creates two similar objects. It's the same idea here. Now below is a table. I think it would be very helpful if you took a screenshot of this and printed it out to put in your notes, or if you wrote it all out in your notes, but it sums up every type of transformation that we've done. So a line reflection, which is an opposite isometry because orientation is not preserved but distance is. These are everything that it preserves. It has reverse orientation. Obviously we know that because that's what opposite means. And then these are all of the rules for the different types of line reflections that we've done. Point reflection is a direct isometry because it has the same orientation. The letter order stays the same. These are everything that's preserved, and this is the rule. Translations are a direct isometry because it has the same orientation. This is everything that's preserved, and this is the rule. Rotations are a direct isometry because it has the same orientation. This is everything that's preserved, and these are the rules, 90 degrees, 180, and 270. If you just memorize the rotation 90 degrees, you can do it twice to get 180 and 3 times to get 270. Same thing if it's negative 90, that's the same thing as 270 counterclockwise. 180 and negative 180 are the same, and negative 270 would be 90 degrees counterclockwise. It's always counterclockwise if you want to make a note to yourself here. If it's not stated specifically, it's always counterclockwise. Dilations are not an isometry or not a rigid motion. Isometry and rigid motion mean the same thing, but the figures are similar, so the preimage and the image will be similar to each other. This is everything that's preserved, so everything is preserved except for length. It has the same orientation, and this is our rule. Keep in mind that if it's not stated what the point reflection is about, or what the translation is about, what the rotation is about, what the dilation is about, if anything is not stated, it's always about the origin, and that's usually going to be what we're working with. Translations are always just in whatever direction, but point reflections, rotations, and dilations are always about a point. If it's not stated, it's the origin. And rotations, it's always assumed that it's rotating counterclockwise unless otherwise stated.